Every time you type something into ChatGPT and hit enter, you are triggering one of the most expensive, most carefully engineered systems humans have ever built to answer a question. Amazon, Microsoft, Google, and Meta are on track to spend roughly 725 billion combined on capex in 2026 alone, up 77% from about 410 billion just last year. Zoom out further, and McKinsey estimates the world will need to pour close to $7 trillion into data center infrastructure by 2030 just to keep pace with compute demand. Somebody has to design that infrastructure, keep it running, and keep the bill from exploding. That somebody is increasingly not a machine learning researcher, it is a systems engineer, an SRE, a DevOps person, a data engineer. So, in this video, I want to open up what actually happens between the moment you press enter and the moment an answer appears. GPU by GPU, server by server, all the way up to the routing layer that decides which machine even gets your request. You don't need a machine learning background for any of this. If you can follow a request moving through a system, you can follow this whole video. The app versus the model. ChatGPT is really two things glued together into one name. There's the chat part, that is the app, the website, the thing you click on. And there is the GPT part, that's the model, the actual thing doing the thinking behind the scenes. GPT is just one brand of the model. Anthropic has Claude, Google has Gemini, Meta has Llama, and there are dozens more. Different names, different companies. But underneath every one of them is the same basic idea, a model that does the thinking wrapped in an app that makes it usable. So, what actually is a model? Forget AI completely for a second. Picture a barista who has one job. You tell her how many shots of espresso you want, and she hands you back a price. One shot, $3, two shots, 4.5. She's basically running a tiny formula in her hand. A starting price plus some amount per shot. That amount per shot, let's say $1.50, is the one number that decides her whole pricing behavior. In AI terms, that number has a name. It is called a weight. It's just a number that system has learned matters, multiplied against something. Change that number from $1.50 to $2, and the exact same formula now gives you completely different prices, with zero change to the structure of the formula. Same shape, different number, different behavior. That's the entire idea behind learning in AI. Nobody handwrites these numbers. Instead, you show the formula thousands of real examples, thousands of past orders, and their actual prices, and it works out which number fits best. That process of finding the right number from example is called training, from one weight to a whole menu. One number gets you a barista who can price espresso shots. It doesn't get you very far. Now imagine she is pricing a full customized drink. Size, number of shots, flavor syrups, oat milk or not. Each one of those ingredients pushes the final price up or down by its own specific amount. That is still just multiplying and adding. The same math as espresso example. Except now, there are dozens of these amount per ingredient, numbers working together instead of just one. Understanding a sentence isn't dozens of these numbers, it is the billions of them, stacked in layers, where the outputs of one layer feeds into the next. Keep stacking that in one very specific arrangement, and you arrive at the architecture behind every major AI model today. It has a name, the transformer. You don't need to know how a transformer works internally. What matters is what it is. The same basic idea as our Barita's pricing formula inputs, multiplication, weights, output. Just enormous and wide in a particular pattern. That pattern, the transformer, is roughly the same piece of code across GPT, Claude, and Llama. What actually makes them different from each other is in the formula. It is the weights. What is actually inside the file? So, all of a model's knowledge lives in those weights, and there are billions of them. They have to be stored somewhere, and that somewhere is quite literally a very large file sitting on a desk. Open it up, and that's genuinely all you would find numbers waiting to be poured into the formula. These files come in widely different sizes. A small model might be a couple of gigabytes. A mid-sized one might be around 16 gigabyte. A large model with tens of billions of parameters can run well past 100 gigabyte, and the biggest frontier models, hundreds of billions of parameters, stretch into several hundred bytes. To actually use one of these files, You load it off the disk into memory. Feed it your question. Let the formula run all those numbers against what you typed, and out comes the answer on your screen. Load the file, feed it text, get text back. At its simplest, that's a model running. Why you can't just run this on your laptop? If a model is just a file and running it is just loading into memory and doing same math, why can't you run one on your laptop? Same models, sure, you actually can. But to see why the bigger ones fight back, we need to look inside a computer. Every computer has two parts we care about here: the processor, the part that actually does the thinking and calculating, and the memory, where the computer keeps whatever the processor is currently working on. Those two live in separate physical places connected by a narrow channel between them. Take the simplest possible calculation: 6 into 7. Both numbers land in the memory first. The processor reads them out, multiplies them, and writes 42 back into memory. Every calculation is that same round trip. One barista versus 100 trainees, CPU versus GPU. Now think about what a model is actually doing under the hood. Billions of tiny multiplication, and critically, these multiplications don't depend on each other. They can all happen at once in parallel. A regular processor, the CPU, is like one incredibly skilled senior barista. She is a brilliant generalist. She can make anything handle any complicated custom order, and she does it fast, one drink at a time in sequence. For almost everything your computer does, your browser, your apps, your operating system, that is exactly what you want. But hand her 100,000 identical, independent little tasks, like add exactly one pump of vanilla to each one of these 10 cups, and she will get through them, but one at a time. And you will be waiting for a very long time. That's the mismatch. The work is massively parallel. The senior barista is built for sequential work. What you actually want is 100 trainees, each one only knowing how to do one tiny step, all working at the same exact amount. That's a GPU. Instead of a few powerful cores, it has thousands of small, simple ones, all doing math simultaneously. A modest GPU can run roughly 100 times more operations per second than a CPU, simply because it trades a few generalists for an army of specialists working in parallel. Why GPUs need their own fridge? VRAM. Solving the speed problem creates a new one. All those trainees need ingredients delivered to them constantly, or they just stand there idle. In a new model, the ingredients are the weights, all those billions of numbers. If you leave them sitting in the computer's regular memory, there is a problem. That memory sits physically far from the GPU, connected by a relatively narrow channel. It's like your walk in storage room being down the hall and around the corner. The fine for one barista grabbing milk occasionally. Hopeless for 100 trainees who all need something right now. So GPUs get their own memory built directly onto the card, sitting right next to the cores, like a small fridge tucked directly under the counter instead of a storage room down the hall. This is called VRAM. It moves data at a rate measured in terabytes per second rather than gigabytes. The catch: that under counter fridge is small. A modest GPU might only have a 16 GB of VRAM. A large model needing 100 plus gigabytes of weight simply won't fit in, which means every GPU you will ever encounter is really described by three numbers: compute, how much math it can do; capacity, how much fits in its memory; and bandwidth, how fast it can read that memory. Every new generation of GPU pushes all three higher, turning the chip into a server. A chip on its own does nothing. Something has to drive it. That is software like PyTorch, which loads a mole's weight onto the GPU and puts all those cores to work. In just a handful of lines of code, you can load a model and ask it a question. But that's a script. It runs once for one person and it's done. Real usage means thousands of people hitting the same model at once constantly. You need something always on, listening for requests. That is a model server. And the one we'll focus on is vLLM, built on top of PyTorch. It wraps the model in a normal web API, the exact same format OpenAI's API uses. So any tool built for OpenAI can point at your own server without changing a line of code. One important detail: a single running vLLM server holds the entire model in GPU memory the whole time it's up. If one server isn't enough, a second one means another full, expensive copy of the model on another GPU. A mall server is a heavy, expensive thing to duplicate. Tokens, the unit everything is measured in. Before going further, one term you will hear constantly: tokens. A model doesn't read or write whole words the way we do. It breaks text into smaller pieces called tokens, roughly three quarters of a word on average. Sometimes a whole word is one token. Sometimes a word split into two or three. An 8 word sentence might come out to around 9 or 10 tokens. Everything gets counted this way: what a model can read at once, what you pay for, and how fast an answer comes back. All of it is measured in tokens. How a model actually writes an answer. A model has exactly one trick. Given all the text so far, predict the single next token. Then it adds the token to the text and predicts the next token over and over until the answer is complete. So a 100 token answer isn't one big calculation. It is this loop running 100 times, one token per lap. That is exactly why ChatGPT's answer appeared to type itself out. You're watching each lap of the loop finish in real time. The streaming effect is a free side effect of how the model actually works. Two things fall out of this. First, these requests take real time. A normal web request finishes in milliseconds, but a few hundred tokens means a few hundred laps of that loop. Second, no two requests cost the same. What is the capital of France? Is a handful of tokens in one or two out. Summarize this 100-page contract is tens of thousands of tokens. Both hit the same server through the same API, but one is 1,000 times heavier than the other. The pause and the pour. Prefill versus decode. Paste a long block of text into ChatGPT and hit enter. And you will notice two distinct phases: a short pause, then the answer streaming out steadily. The pause happens because before the model can write a single word, it has to read the entire prompt first. Since your whole prompt already exists, there's nothing to wait on. Every token gets pushed through the model together in one big burst with thousands of GPU cores firing at once. That burst ends by producing the very first token of the answer. This phase is called prefill. The length of the pass it causes is called TTFT, time to first token. A 7 token question causes a barely noticeable pause. A pasted 100-page contract creates a real measurable one. The pour is the second phase, the token by token loop, writing the actual answer. Each new token requires one full pass through the model. And here's the catch: to produce even one token, the GPU has to read the entire model out of its memory. Write a $200 token answer, and you've loaded the whole model out of memory 200 separate times, once per token. This phase is called decode, and its speed is capped by how fast the GPU can read its own memory, not by how much raw compute it has. The gap between consecutive tokens is called time per output tokens. On fast hardware, that gap can be just a few milliseconds per token. But it is a hard physical ceiling set by memory bandwidth, not something you can just add more compute cores to fix. The ticket rate, KV cache. Here's a question: if prefill is expensive and decodes requires rereading the whole model for every single token, why doesn't every new word cause a fresh, painful pause? Why does ChatGPT stream smoothly instead of stuttering before every word? Think of a busy kitchen's ticket rate. The moment an order's prep work is done, vegetables chopped, sauce started, it doesn't get thrown away and redone for every single plate that goes out on that ticket. It sits on the rail, ready to be reused. That is exactly what happens with prefill. The expensive first pass gets saved directly in GPU memory instead of being discarded. This saved work is called the KV cache. Prefill runs once at the start and its output goes into that cache. From then on, Decode doesn't repeat prefill for every new token. It just reaches into the cache, reuses everything already worked out, and add one new token on top. You pay for the pass exactly once, not once per word. Remembering regular customers, prefix caching. Here's the catch with the ticket trail. The moment your order is fully plated and out the door, the ticket gets clear. Send a second chat message, and the model remembers nothing from before. Your app quietly resends the entire conversation from scratch every single time, and the server has to reread all of it before it can reply. The longer the conversation, the longer that reread takes over and over. So, what if instead of clearing the ticket the moment it is done, you kept it, labeled exactly by the text that produced it? Send message to, and the model recognizes it's already done the work on everything except your newest line. That is the only part it has to process fresh. Message 10 ends up costing roughly what message 2 cost. This is called prefix caching. It is why in Anthropic's own API console, there is a setting called prompt caching, and a cached input token costs a small fraction of what a fresh one costs. If you're building anything that repeats the same long instructions at the start of every call, like a company wide assistant that opens every conversation with the same system prompt, this is a direct, meaningful cost saving because that shared opening block gets computed once and reused for every single person who talks to it, not per person. The batch order, here's the earlier insight again. Producing even one tokens means rereading the entire model out of memory. If the GPU has to do that expensive read to produce one token for one customer, why not use that same read to produce a token for 50 customers at once? That is batching. Instead of serving orders one at a time, you group many people's requests together and run them through the GPU as a single batch. Same way, a barista steams milk for 10 lattes in one pass instead of 10 separate ones. Each person's own answer come out at roughly the same speed it would individually. But the server's total output, its throughput, shoots up dramatically. You end up serving 50 people something close to the cost of serving one. Without batching, nobody could afford to run this hardware profitably. Why the counter runs out of the space first? Why not batch a million users onto one GPU? The limit is memory, not raw processing power. Every single person in a batch needs their own KV cache, sitting in GPU memory for as long as they are being served, their own little prep station on the counter. That memory is small to begin with, and most of it is already claimed just holding the model's weights. Whatever is left over is the only counter space available for everyone's individual prep work. Fill that space, and the server is full. No people wait in line, or someone else saved work gets evicted to make room, which is exactly why ChatGPT sometimes tell you it is at capacity. Notice what is in the bottleneck. The processing cores usually have plenty of idle math capacity left. It is memory that decides how many people one GPU can actually serve. And this is also where a lot of real money gets wasted, with teams buying far more GPUs than the math actually requires, while those expensive cards sit half idle. When one counter isn't enough, sharding giant models. Memory doesn't just decide how many customers fit, it also decides whether the model fits on a single GPU at all. The very largest model, with hundreds of billions of parameters, are simply too big for a single card to hold, even one with 80 plus GPU of VRAM. The fix, bring in several GPUs, slice the giant model into pieces, put one piece on each card. No single GPU holds the whole thing, but together they do. This is called sharding, and vLLM can handle it largely on its own. Point it at a giant model. Tell it how many GPUs are available, and it splits the work. There are two ways to slice a model. The first is by layer. GPU 1 gets the first set of layers, GPU 2 gets the next set. The second works within a single layer. You split that layers calculation in half, and two GPUs each do half the work before combining their results. The pass through, window versus walkie-talkie. Which slicing method you use depends entirely on how fast the connection is between the GPUs. Inside a single machine, GPUs are connected by an ultra fast link called NVLink, like a direct pass through window between two stations in the same kitchen. They can afford to talk to each other constantly, so the chattier method, splitting within each layer, works beautifully there. Pack 8 GPUs into one box on that fast link, and they can serve a giant model as if they were one machine. Go bigger than a single box, though GPUs sitting in different physical machines, and all you have is ordinary network between them. Much slower, more like a walkie talkie between two different shop locations across town. Constant back and forth chatter doesn't work over that connection. So you switch to the quieter method. Whole stretches of layers handed off, with each machine passing along just one result to the next. Keep the chatty talk inside a box and keep the quiet talk between the boxes. The fleet and why a regular load balancer breaks it. Sharding solves the fit on one GPU problem. But real service isn't run on one server. You need a whole fleet of them, each an expensive GPU server carrying its own copy of the model. So, how does your request find its way to the right? The obvious instinct, if you have worked in infrastructure before, is to put a standard load balancer in front and spread requests evenly, round robin, one to each server in turn. We've balanced web traffic this way for decades. For serving language models, it turns out to be the wrong move for two reasons. Reason one, say your first message lands on server 2, which reads your conversation and saves it KV cache in memory. Your second message arrives, but the load balancer's whole job is spreading things evenly. So it sends this one to server 5 instead, which has never seen you before and has to reread your entire conversation from scratch. The load balancer treats every server as interchangeable. They are not. It just threw away perfectly good saved work on the most expensive hardware in the building. Reason 2, a load balancer assumes every request is roughly the same size. But one might be hello, next might be summarize these 50 pages. To the load balancer, both look identical, same address, same kind of traffic. It might route that 50-page request straight into a server that's already busy streaming answers to 30 other people, and all 30 of them slow down. A regular load balancer has no visibility into how full each server's memory is, whose saved work is sitting where, or how long each queue is, because all of that live inside the servers, invisible from the outside. LLM-D. This is the exact wall that stopped everyone in the industry, which is why several major companies, including Red Hat, Google, IBM, and Nvidia, decided to solve it together in the open. What they built is called LLM-D. At its core, LLM-D is a smart router sitting in front of your entire fleet. Think of it as a head waiter who actually remembers who is sitting where, instead of a host mechanically seating people in rotation. When a request comes in, it looks at three things before deciding where to send it. First, saved work. LLM-D tracks which server holds which conversations cached prefill work and routes your next message straight back to the server that already has it, skipping the reread entirely. Routing this way, instead of spreading evenly, can multiply overall throughput several times over on the exact same hardware, while also cutting the first response wait roughly in half. Second, real capacity. It checks how full each server's memory actually is and how long each queue is sending your request somewhere with genuine room instead of piling onto a server that is already full. Third, splitting the two very different jobs. Prefill is compute heavy, Decode is memory bandwidth heavy. On one shared GPU, they take turns, and a big prefill can make everyone else answer stall midstream. LLM-D can split them onto separate pools, one pool that does nothing but prefill, another that does nothing but decode, each running hardware suited to its job. When a prefill server finishes reading a prompt, it hands that saved cache across a fast link to a decode server, which streams the response back. The platform underneath it all, Kubernetes. Here's the part that should feel familiar. If you already work in infrastructure, LLM-D runs on top of Kubernetes, the same platform that most teams already use to run everything else. According to the 2026 CNCF Annual Cloud Native Survey, 82% of the container users now run Kubernetes in production, and 66% of organizations hosting generative AI models already use it to manage some or all of their inference workloads. It has quietly become the default choice for this exact job. Each vLLM instance runs as a pod, landing on whichever node has room. A group of identical pod is a deployment. One deployment for your prefill pool, one for your decode pool. In front sits a gateway, giving you a single address for the whole fleet. And just behind it sits the LLM-D scheduler, holding the cache aware, load aware, routing logic. The gateway takes the request. The scheduler picks the pod. For giant sharded models, Kubernetes need a way to treat a whole group of pods, one model split across several GPUs, as a single unit, not as an independent replicas. A regular stateful set doesn't quite fit because those pods aren't separate copies of anything. Together, they are one server, just split into pieces. Kubernetes solves this with an object built for exactly this case. A leader pod plus its workers scaled and healed together as one unit. You describe all of this, the model's location, how many prefill pods, how many decode pods in a single configuration file, apply it, and Kubernetes build the whole fleet. Pods, gateway, scheduler, wired together. And once it is running, the normal Kubernetes loop keeps watching over it, restarting crashed pods, moving work off dying machines, letting you scale the prefill and decode pools independently as your traffic shifts. The full path of a request. Let's put the whole thing together. You send a message, it hits the gateway, the scheduler picks the path that already holds your saved conversation cache, a prefill server reads anything new in your prompt, a decode server streams the answer back to your one token at a time straight out of the memory. If the model happens to be a giant, several GPUs across multiple machines just did that work together as one. Wrap up. Why this is your opportunity? Look back at everything we just covered: pods, deployments, routing, caching, batching, memory, networking. Almost none of it was machine learning. It was infrastructure work, start to finish. If you're a systems administrator, an SRE, a DevOps engineer, or a data engineer, you're already close to this world than you might think. The models are new. The discipline, Linux, containers, Kubernetes, monitoring, capacity planning is exactly what you already have, and is exactly what companies racing to ship AI are struggling to hire for. You don't need to become a data scientist or train models from scratch. You need to point the skills you already have at a new kind of workload, keeping the GPUs busy, the latency down, and the bill under control. That's it for this one. If this kind of breakdown is useful, let me know what part of the AI infrastructure stack you want me to go deeper on next. And don't forget to subscribe. See you in the next video.